Today, I will present a comprehensive analysis of GABAergic neurotransmission and its pharmacological modulation in anxiety disorders. This video will focus extensively on the molecular mechanisms of actions of three primary drug classes that target the GABA system, which are benzodiazepines, barbiturates, and neurosteroids. We will examine their distinct binding sites, allosteric modulation patterns, and clinical implications in anxiety pharmacotherapy. Remark that there are two types of neurotransmitter, excitatory and inhibitory. GABA or gamma-aminobutyric acid serves as the principal inhibitory neurotransmitter in the central nervous system, functioning as a neuronal brake that regulates excitatory signaling. In anxiety disorders, GABAergic dysfunction manifests as impaired inhibitory control over hyperexcitable neural circuit, particularly in the amygdala, prefrontal cortex, and hippocampus. The biosynthesis of GABA occurs through decarboxylation of glutamate by glutamic acid decarboxylase, known as GAD, utilizing pyridoxal phosphate, known as PLP, which is the active form of vitamin B6 as an essential cofactor. Following synaptic release, GABA undergoes reuptake via GABA transporter GAT1 in neurons and GAT3 in glial cells, before metabolic degradation by GABA transaminase known as GABA-T and succinic semialdehyde dehydrogenase known as SSADH. The GABAergic system operates through two primary receptor subtypes: ionotropic GABA-A receptors, which mediates fast synaptic inhibition through chloride conductance, metabotropic GABA-B receptors, which provides slower, prolonged inhibition via G-protein coupled mechanisms. GABA-A receptors exist as heteropentameric assemblies, most commonly composed of alpha-1, beta-2, gamma-2 subunits, which account for approximately 50% of all GABA-A receptors in the brain. Now, let us look at the action of three primary drug classes that target the GABA system. Benzodiazepines. Benzodiazepines exert their anxiolytic effect through positive allosteric modulation of GABA-A receptors. The benzodiazepine binding site is located at the alpha-gamma subunit interface, specifically requiring the presence of both alpha-1, alpha-2, alpha-3, or alpha-5 subunits paired with any beta subunit and the gamma-2 subunit. This site represents a high-affinity binding domain distinct from the GABA orthosteric site. The benzodiazepine pharmacophore consists of a benzene ring fused to a 7-member diazepine ring. Critical structure-activity relationships include the presence of an electronegative substituent at position 7, which correlates with receptor affinity, an aromatic ring at position 5, which affects binding kinetics, and the overall planarity of the molecule, which is essential for proper receptor interaction. Upon benzodiazepine binding, conformational changes occur in the alpha-gamma interface that enhance GABA's binding affinity and increase the frequency of chloride channel opening events. Specifically, benzodiazepines increase channel opening frequency by 3 to 5-fold without affecting single channel conductance or mean open time. This represents a classic example of positive cooperativity, where the modulator enhances the natural ligand's efficacy without directly activating the receptor. The molecular mechanism involves several key steps. First, conformational stabilization. When a benzodiazepine molecule binds to its specific site on the GABA-A receptor, it locks the receptor into a conformation that favors GABA binding. Next up is pre-activation enhancement. Once benzodiazepine has stabilized the receptor, it makes it easier for the channel to move from a closed state into a pre-open state. Finally, we have gating facilitation. Because the receptor is already stabilized and pre-activated, the coupling between GABA binding and pore opening becomes much more efficient. In other words, when GABA finally binds, the ion channel has a higher probability of opening fully. This leads to an increased influx of chloride ions, hyperpolarizing the neuron and producing that calming anti-anxiety effect we associate with benzodiazepines. Different alpha subunit compositions confer distinct pharmacological profiles. Alpha 1 containing receptor mediates sedative and amnestic effects. These receptors show high sensitivity to zolpidem and are responsible for the hypnotic properties of most benzodiazepines. Alpha 2 containing receptors are primary mediators of anxiolytic effects. These receptors are enriched in limbic structures and show preferential sensitivity to certain benzodiazepines. Alpha 3 containing receptors contribute to muscle relaxant properties and are abundant in spinal cord and brainstem. Alpha 5 containing receptors, which are located primarily in hippocampus, mediate cognitive impairments and memory disruption associated with benzodiazepine use. Chronic benzodiazepine exposure leads to adaptive change in GABA A receptor expression and function. Key mechanisms include the follows. First, alpha 2 subunit downregulation. Chronic exposure specifically reduces alpha 2 subunit expression at GABA A receptors, which gradually diminishes the anxiolytic efficacy of the drug. Next, receptor internalization. Prolonged agonist binding promotes endocytosis and degradation of GABA A receptors, lowering the number of functional receptors available at the synapse. Finally, compensatory upregulation. To counteract the enhanced GABAergic tone, the brain increases expression of excitatory system, such as glutamate and norepinephrine pathways, ultimately contributing to tolerance and withdrawal symptoms. Now, let's look at the barbiturates. Barbiturates bind to multiple homologous transmembrane pockets located within the transmembrane domain of the alpha and beta subunits, distinct from both GABA and benzodiazepine binding sites. Unlike benzodiazepines, barbiturates modulate channel gating through two distinct mechanisms: GABA-dependent modulation and direct channel activation. First, let's talk about GABA-dependent modulation. At low concentrations, barbiturates enhance GABA-activated currents by prolonging channel open time rather than increasing opening frequency. This effect involves stabilization of the open channel conformation through interactions with the transmembrane beta subunit regions. And the next one is direct channel activation. At higher concentrations, barbiturates can directly activate chloride channels in the absence of GABA. This GABA-independent activation occurs through conformational changes that mimic GABA binding, leading to channel opening without requiring the endogenous neurotransmitter. The barbiturate dose-response relationship exhibits several distinct phases. At low concentrations, about 1 to 10 micromole, there is selective enhancement of GABA-activated currents with minimal direct activation. At intermediate concentrations, about 10 to 100 micromole, you see mixed effects, with both GABA potentiation and some direct activation of the receptor. And at high concentrations, which is more than 100 micromole, direct activation predominates, leading to profound CNS depression. This concentration-dependent mechanism explains the narrow therapeutic window and high overdose potential of barbiturates compared to benzodiazepines. Barbiturates have additional molecular targets beyond GABA-A receptors. First, AMPA receptor antagonism. Barbiturates suppress glutamatergic excitation by blocking AMPA receptors, contributing to their anticonvulsant properties. Next, voltage-gated sodium channel inhibition. High-frequency neuronal firing is suppressed through sodium channel blockade, particularly relevant for their anti-epileptic effects. Finally, calcium channel modulation. Barbiturates can affect both L-type and N-type calcium channels, influencing neurotransmitter release. Chronic barbiturates exposure induces cytochrome P450 enzymes, particularly CYP2B and CYP3A subfamilies. This enzyme induction leads to enhanced metabolism of the barbiturates itself increased clearance of co-administered drugs being potential for significant drug-drug interactions, and development of metabolic tolerance. Finally, let's take a look at neurosteroids. Neurosteroids represent a paradigm shift in GABAergic pharmacology by targeting extrasynaptic GABA A receptors containing delta subunits. These receptors, typically composed of alpha 4 beta 3 delta or alpha 6 beta 3 delta subunits, are located outside synaptic clefts and mediates tonic inhibition rather than phasic synaptic transmission. The delta-containing receptors exhibit high GABA sensitivity, responding to ambient GABA concentrations, which is 1 to 5 micromole. They also display slow desensitization, maintaining prolonged activation alike synaptic receptors. These receptors are insensitive to benzodiazepines, as they lack classical benzodiazepine binding sites. Additionally, delta-containing receptors show selective neurosteroid sensitivity, demonstrating exceptional responsiveness to endogenous neurosteroids. The neurosteroids pharmacophore requires a 3-alpha hydroxyl group, which is essential for effective GABA A receptor binding and activation. Compounds with the 3-beta hydroxyl configuration exhibit markedly reduced or absent activity. A 5-alpha reduced steroid backbone featuring a saturated A ring is necessary for optimal receptor interaction and potentiation. Additionally, high lipophilicity is crucial as it enables rapid brain penetration and efficient membrane partitioning necessary for neurosteroid efficacy. Allopregnanolone is the most potent endogenous positive modulator. Pregnanolone is a stereoisomer with similar but distinct activity. THDOC, which is 3-alpha 5-alpha tetrahydrodeoxycorticosterone, is a corticosteroid-derived neurosteroid. Neurosteroids exerts a dual mechanism of action encompassing both rapid non-genomic effects and slower genomic effects. In terms of non-genomic effects, neurosteroids directly bind to transmembrane domains of delta-containing GABA A receptors, enhancing channel open time by up to 10-fold and modulating channel conductance properties. They also interact with sigma-1 receptors, which influences intracellular calcium signaling within seconds to minutes. In contrast, their genomic effects unfold over hours to days. Neurosteroids activate classical steroid hormone receptors, leading to enhanced transcription of BDNF and other neuroplasticity-related genes. They also modulate inflammatory pathways by inhibiting NF-kappa B and induce long-term changes in GABA A receptor expression patterns. Neurosteroids exhibit rapid brain penetration as their high lipophilicity allows immediate CNS access. They preferentially accumulate in myelin-rich brain regions, reflecting their unique tissue distribution. Metabolism occurs primarily in the liver via 3-alpha hydroxysteroid dehydrogenase. Finally, they undergo relatively rapid clearance, necessitating continuous infusion for sustained effects. Now, let's wrap up this whole video. This whole video demonstrates the anxiety pharmacotherapy involves sophisticated modulation of GABAergic neurotransmission through distinct molecular mechanisms. Benzodiazepines enhance synaptic inhibition through allosteric modulation, and barbiturates provided both enhancement and direct activation with associated risks, while neurosteroids offer a novel approach targeting tonic inhibition with neuroplasticity benefits. Understanding this difference is crucial for optimizing therapeutic outcomes, minimizing adverse effects, and developing next-generation anxiolytic agents. This evolution from barbiturates to benzodiazepines to neurosteroids represents progressive refinement in targeting specific components of the GABAergic system for anxiety treatment.